In this tutorial, we'll consider a 2D force problem involving an object on a horizontal surface. Our example, a 100 kilogram box is sitting on a floor. The coefficient of static friction between the box and the floor is 0.40. What is the force applied at a 30-degree angle above the horizontal, as shown, required to get the box to start moving? First step, a good free body diagram, always. We have Fg down, F normal up, and we have our applied force at 30 degrees here. And finally, we have the friction force opposing the motion of the box along the surface. Let's consider our situation here. The fact that Fa is applied at an angle impacts a couple of things. The greater the angle, the more the normal force is changed. The fact that part of this force is pushing down on the box means that the normal force is increased. Not only does the floor have to support the force of the box's weight, but it also has to counter the fact that the person is pushing down on the box. So, our normal force is going to be bigger than our Fg, meaning that our frictional force is increased as well. Back to our solution. We have a nice free body diagram, so next we write Fnet equals ma, recognizing Fnet as the sum of all the forces on our left, and on the right we're looking for the point where it's just overcoming the friction force, causing the movement to start. So A equals 0, meaning that our Fnet, or all the forces involved, are all going to add up to 0. So let's consider our method of solving this. Vector trig method or component method? Well, if we choose the vector trig method, we'll add up all the vectors on the left in a vector diagram. Fg going down plus tip to tail, Ff, or the force of friction, going left plus tip to tail. We have our normal force going up, and we know that Fn is bigger than Fg as discussed, so we'll draw this vector a bit longer. And finally, our applied force, Fa, which goes back to the beginning, as Fnet equals 0 means that the end of our vector addition is exactly where we started, a resultant vector of 0. We can see that the y component of Fa causes the difference between Fg and Fn, as we discussed. And we can also see that the x component of Fa is what's countering our friction force horizontally. Anyway, though not a triangle, we could definitely do a little geometry and solve for Fa using our vector trig method. Given that, many people would choose to attack the problem using components. So let's switch to that direction. We'll split our problem into two directions along the x-axis and then along the y-axis. In the x direction, we'll start with Fnet x equals max. Our forces in the x direction on the left include Fax going to the right, or positive, and the force of friction, Ff, going left, which will be negative. On the right side of the equation, we know that Ax equals 0, as we're just initiating the movement. So, Fa cos 30 minus Ff equals 0, or we can arrange and solve for Fa. We might be tempted at this point to replace the Fn with mg, but that would be wrong in this case. Remember that the Fa also adds to the normal force. Thus, we better switch to the vertical direction and determine more about that. In the y direction, Fnet y equals may. Our forces in the y direction include Fn going up, or positive, Fg going down, or negative, and the y component of Fa, or Fay, is also going down, or negative. On the right side of the equation, we know that Ay is 0, as there's no vertical movement or acceleration. So we can rearrange to see that Fn equals Fg plus Fay, or we can rearrange and solve for Fn. And then we can add some detail to that. And we can combine our equations, and then rearranging for Fa and substituting in some numbers, we get Fa equals 589 newtons, with a little rounding. So, to get this box moving, our angled force would need to be greater than 589 newtons. In this tutorial, we took a look at a 2D force problem that involved an object sliding on a horizontal surface. We noticed how the Fa at an angle impacts the normal force, which in turn impacts the friction between the surfaces. We took a look at a vector diagram that could lead to a solution using the trig vector method. We then switched to the component method, which is a more typical solution for this type of problem. We developed an equation while considering the forces in the x direction, and then another equation while considering the forces in the y direction. These two equations, when combined, provided us with a nice solution to the problem. We were able to determine the force required to make the box move.